the triangle XYZ is right angled at X, and XP is perpendicular to YZ, as you can see. YP is 4, PZ is 8, and the distance of P to X is K. We want to find the value of K. Well, we've two right angled triangles here. So we have the two short sides, well, in terms of K, of this particular right angled triangle. So let's get the hypotenuse of this triangle. Well, it's going to be the square root of the sum of the squares of the two short sides. It's going to be root 4 squared plus k squared. That's root 16 plus k squared. Now what about the hypotenuse of this right angled triangle? Well, it's root 8 squared plus k squared. That's root 64 plus k squared. Now we can consider the big right angled triangle. We have the hypotenuse of it. That's the side opposite the right angle in the big triangle. It's 8 plus 4, which is 12. So the three sides are connected by Pythagoras' theorem, and we only have one unknown, so we can find it. So if we take the sum of the squares of the two short sides, what do we get? Well, if we square each of these and sum them, we get 16 plus k squared plus 64 plus k squared. So 16 plus 64 is 80. K squared plus k squared is 2k squared. Okay, so squaring these and summing them, we get this expression. And squaring the hypotenuse gives us 144. So subtract 80 from both sides to get 64. Divide both sides by 2 to get 32. So we see that k is the square root of 32. The shaded region in the diagram below is called an Arbelos. It is a plane semicircular region of radius r1 from which semicircles of radius r2 and r3 are removed as shown. So in the diagram, SC is perpendicular to AF and the distance of S to C is K. Show that for fixed R1, the perimeter of the Arbelos, so we want the distance all around the shaded part, is independent of the values of R2 and R3. Okay, so part of the perimeter of the Arbelos is the distance all around this semicircle of radius r1. Now the distance around a full circle of radius r1 is 2 pi times the radius. That's a full circle. But if we just want the distance of A to F, we have to get half of this. That's just pi times r1. Okay, so I'll indicate that on the diagram. So this distance is pi times r1. So this is the distance as far as from F to the point A. Now, what about this distance here? Well, again, we have a semicircle. This perimeter or circumference of a full circle is 2 pi times the radius. So since we just have half a circle, it's just pi times the radius. The radius of this semicircle is r2. And what about this one here? Well, in a similar way, we multiply pi times the radius. The full circle would be 2 pi times the radius, so this is this distance here. So to get the perimeter of the Arbelos, that is the shaded region, we just have to add these three quantities together. It's pi r1 plus pi r2 plus pi r3. We can factorize pi out of this, of course. So we have pi into r1 plus r2 plus r3. So the sum of the three radii. Now we want to show that this perimeter is independent of r2 and r3. So r2 and r3 should not appear in this. We should have an expression that just involves r1 as the radius of the big semicircle. Okay, so let's see if we can somehow replace r2 and r3 with something involving r1. So then our expression will not depend, that is, it will be independent of r2 and r3. Okay, it'll have to depend on r1, of course. It can't, we can't just have a pure number here because, r1 can be any value. Okay, so let's get the connection between the radii. Well, we can consider the total distance here. Total distance along here. This is the diameter of the large circle. So that distance is just twice the radius. So it's 2r1. Okay, but this diameter is made up of twice the radius of this circle plus twice the radius of this circle here. So this is 2r2, and this distance here is 2r3. So we can see that 2r1 is just 2r2 plus 2r3. So if we just divide this by 2, we can see that we can get r1 in terms of r2 and r3. So we can replace r2 plus r3 with r1. Okay, so r1 goes in here. So we end up with 2 r1 times pi. Okay, I'll write it as 2 pi r1. So we found the perimeter of the Arbelos in terms of the radius of the large circle. So it does not depend on the radii of the two smaller circles. If R2 is 4 and R3 is 4, show that the area of the Arbelos is the same as the area of the circle of diameter k. So we want to make R2 equal to 2. And we want to change R3 to equal 4. Now let's get the area of the Arbelos. Well, what's the diameter going to be? Well, we saw in the previous part that R1, the radius of the big circle, is R2 plus R3, 2 plus 4, which is 6. So we can get the area of the big semicircle, and then we need to subtract out these two smaller semicircles. Okay, the area of a full circle is pi r squared, so we have half a circle. So that's 36 divided by 2 is 18, so it's 18 pi. And we have to take the area of the big circle and subtract out the area of the two smaller circles. Okay, so we want the area of this one here. Well, this one here is going to be a half pi times the radius squared, and this one is going to be a half pi times 4 squared. Alright, so this is 2 pi, and this one here is 8 pi. So we want to subtract out these two values, so 10 pi in total. So we get 8 pi. Next we want the area of the circle whose diameter is k. Now, so this distance is 4, 2 and 2, and this distance is 8, 4 and 4. What is k? Okay, we can find that by actually referring back to the first part of the question. We have a very similar situation. This line here perpendicular to this line. Just like here, the line SC is perpendicular to the line AF. And we found out what k was from the first part. It was the square root of 32. So we have the diameter of our circle. Okay, so we have a circle whose diameter is k. And we want to get the area of that circle. Well, the area of a circle is pi r squared. So if the diameter is k, the radius, if the diameter is root 32, the radius is root 32 divided by 2. So this is going to give us 32 over 4. Well, that's 8. So that isn't. So the area of the circle of diameter k is indeed the same as the area of the Arbelos. So a circle standing on the line k, okay, a circle with a diameter equal to the length of the line k has the same area as the Arbelos, the shaded region. It's quite interesting. To investigate the area of an Arbelos, a student fixed the value of R1 at 6 centimeters and completed the following table for different values of R2 and R3. So R1 remember, is the area of the big semicircle. R2 was the area of the left semicircle. R3 was the area of the right semicircle. And we calculated the area of an Arbelos for particular values earlier. Okay, we take the area of the big semicircle, that's half pi times the radius squared. Okay, pi r squared is a full circle, so half pi r squared is a semicircle. So we take the area of the big semicircle and subtract off the areas of the two smaller semicircles. So we would have to subtract off a half pi 1 squared and subtract off a half pi 5 squared. Well, we can factorize the half pi out of this. So half pi 6 squared minus a half pi times 1 squared minus a half pi times 5 squared can be written like this. Okay, we can factorize out the minus sign as well. So, we can write this in terms of pi. So we can calculate what's inside the bracket. That's actually 10. 10 divided by 2 is 5. And we can repeat that calculation for these other values. In general, for R1 equals 6 centimeters and R2 equals x, where x is some number between 0 and 6, well, that makes sense, because R2 is the radius of one of the smaller semicircles, and that radius has to be less than the radius of the big semicircle if this smaller semicircle is to fit into the bigger one, of course. Find an expression in x for the area of the Arbelos. So we need the area of the big semicircle. Okay, we will plug in 6 for R1. Now here we subtract off the areas of the two smaller semicircles. The half pi has been factorized out. And of course we can factorize a half pi out of the whole lot. So we get this expression here, which is really what we see up here, So we haven't really done anything new. But what is the relationship between the radii of the two smaller semicircles? Okay, we're saying that the radius R2 is x. So what is R3 going to be in terms of x? Well, that's something that we saw earlier actually. We saw that R1 is equal to R2 plus R3. The radius of the big semicircle is the sum of the radii of the two smaller semicircles. So we are calling R2 x. R1 is 6. R2 is x. So R3 is just 6 minus x, of course. Alright, so we write 6 minus x for R3. So R2 is what we call x. And since R2 plus R3 is 6, R3 must be 6 minus x. And we need to square it. See, it's R3 squared, so we need to bracket 6 minus x and square it. So we'll get an x squared from this term here. We get another x squared here. That's going to give us 2x squared, okay? And we'll divide by the 2 outside, so we'll end up with minus 1x squared. Okay, so we get an x squared from this minus sign. This x squared would be positive, but the minus sign would make it negative, so we'll get a minus x squared is minus 2x squared, and dividing by the 2 outside will give us minus 1x squared. Now, what about the x term? Well, if we multiply 6 by minus x and double, we get minus 12x. And the minus 12x is divided by the 2 outside to give us minus 6x. But there's a minus sign here, so we'll end up with plus 6x. As for the constant term, we have 6 squared here, and the minus sign outside means we end up with minus 36 here. Plus 36 minus 36 is 0. Okay, anyway, so if you simplify all of this down, you'll get 6x minus x squared. And you divide by the half, of course. So that's the area of the Arbelos in terms of x, where x is the radius of the first small semicircle. So what we have here is a formula that gives us the area of an Arbelos of radius 6 centimeters. Okay, that's the big semicircle has a radius of 6 centimeters. And we can vary x. X is the radius of the first small semicircle. Okay, so if we look at the diagram. Let's suppose that the big semicircle is fixed with a radius of 6, and we vary the radius of this semicircle. Okay, we'll obviously vary the area of the Arbelos. So we're keeping the big semicircle fixed, but we're varying x, where x is the radius of this semicircle. Of course, if we vary the radius of this circle, we automatically vary this one. Okay, so here's our expression for the area. So we want to find the value of x that maximizes this expression. Alright, so here's the picture. X is the radius of the first small semicircle. 6 minus x is the radius of the second small semicircle. So this shaded area is given by this formula. So what does the graph of this thing look like? Well, this is a quadratic. Okay, pi is just a number. The x squared term is negative. So the shape is an inverted parabola. The constant term is 0, by the way. You could write this as minus pi x squared plus 6 pi x plus 0. Okay, there's the x squared term, there's the x term, there's the constant. A is minus pi, b is 6 pi, c is 0 in this quadratic function. The constant term is 0, so the inverted parabola goes through the origin. Okay, so when x is 0, a is 0. So we want a value of x that maximizes the area of the Arbelos. We know there's two ways of doing this. We've come across this thing before. We could find the two roots of the equation got by setting this equal to 0. That's the easiest way to do it. So if I set this equal to 0 and solve, well, we can factorize x out. Okay, it's very simple quadratic to solve actually. So I'm finding where the points for which a is 0. So we see that x equals 0 is one of them. Well, we know that. And if we put the other factor equal to 0, we get x equals 6 pi divided by pi. So this is 6, this is 0. So the maximum value of a occurs when x is 3. So when the radius of the first semicircle is 3, the Arbelos has maximum area. Now, of course, the other way to do this is to differentiate. Okay, find the value of x for which the slope is 0. So we could differentiate this expression, set the result equal to 0 and solve. Okay, I'll just squeeze that in over here. Let's suppose I differentiate this thing, so we get dA dx. Well, that's going to give us minus 2 pi x plus 6 pi. So we set the derivative equal to 0 because the slope at this value is 0. So if we solve this equation, we get x equals 3 as before. So two ways to do that. Alright, so at x equals 3 we actually have a maximum. We don't have to do this second derivative test because a is a quadratic function of x, so there's only one turning point, there's only one stationary point of this function. There's only one value for which the derivative is 0. So and it's an inverted parabola. The x squared term is negative, so we have enough information to understand that at x equals 3 we have a local maximum. So x equals 3 gives us the maximum area, not a minimum area, but a maximum area of the Arbelos. As a matter of fact, the minimum would occur when x is 0. If you plug 0 in for x, you get a equals 0. So the minimum value that the area can be is 0. So it's pretty clear from the context that x equals 3 must give us the maximum area of the Arbelos. Okay, and we want to find that maximum area. Well, we plug x equals 3 back into this expression here to find out what the corresponding a is. If we plug 3 in, we get pi times 18 minus 9. That's pi times 9, or 9 pi centimeters squared. And it's easy to look at a sketch of that. Right, we found x equals 3 here. So the radius of the first semicircle is 3. So the first semicircle would stretch to the center of the big semicircle, and the second semicircle will be identical to the first semicircle. Okay, so this is 3, and the second one, well, it's 6 minus 3, which is also 3. AS and FS cut the two smaller semicircles at points T and R respectively. Prove that RSTC is a rectangle. Now this is quite straightforward. So the angle between the line FS and AS is 90 degrees. So this angle up here is 90 degrees because it's the angle in the semicircle. We pick a point on the semicircle and join that point to the ends of the diameter, and so this angle is 90 degrees. Similarly in here, point T is a point on the smaller semicircle. If we connect that point to the ends of the diameter, we have a right angle. So this angle is right angle, so the one next to it is obviously a right angle. So these two angles up here are right angles. And similarly here, of course, point R is a point on the bigger, or this semicircle. So if we connect it to the ends of the diameter, we have a right angle formed here. So the one next to it is obviously a right angle. So the angle up here is a right angle, this angle is a right angle, and so is this one. So the one that's left must be a right angle. Okay, the 4 of them must add up to 360. So this quadrilateral is actually a rectangle.